So we're working a progression of 3D particle equilibrium problems that are getting harder and harder. In this case, previous problem, these guys were symmetric about the x to z axis. In this problem, it's basically a very similar problem, except now we've put a strut on here that's pushing at A. But then these guys are not symmetric about the xz plane. So it's a little bit harder. We write the unit vectors for each one of these guys. So for AB, the line vector from A to B is -6 in the x, -2 in the y, and +2 in the z. That's the line vector. Divide by the length of the line, which is square root of 44, which is 6.63. Again, you can use the unit v function, and you get this is the unit vector for AB. For AC, we write the line vector from A to C, which is -6 in the x, +4 in the y, and +4 in the z. The denominator is the length of the line, which is the square root of 66, which is 8.246. And again, you can use the norm function here, or you can just use the unit v function directly to get this unit vector for AC. The FAD, and this is my free body diagram right here, this point at A. This strut is pushing at A, and so his unit vector is 1 in the x, 0 in the y, and 0 in the z. The weight, his unit vector, is 0 in the x, 0 in the y, and -1 in the z times 100. So these give me all of my unit vectors. In the z direction, I'm going to take the z components. So I have 0.4851 TAC plus 0.3015 TAB minus 100 is equal to 0. In the y direction, I have 0.4851 TAC minus 0.3015 TAB is equal to 0. And you might say this would lead to a 3 by 3, but because of the dimensions of this guy, you actually have similar terms here. And so what we could do is we could either subtract 1 minus 2 to eliminate this term, or we can add the 2, and these two terms with opposite signs will cancel. I chose to add them. And so if you add these two equations, we get 2 times 0.4851 TAC. These guys cancel, and you get 100 on the right-hand side. So you get TAC equals 103.1 pounds. From TAB, you can solve this equation, equation 2 for TAB, and you get 165.9 pounds. Once you have these two, then you can sum forces in the x direction, and you get FAD minus the x component of AB minus the x component of AC equals 0. Plug these guys in here, and you get FAD is 225.1 pounds. And so this is a problem. It's not symmetric, and you might think, okay, I've got to solve a 2 by 2, or I've got to, solve something more complicated. But sometimes this happens where, and you should inspect your equations. And so once you write these equations and you go, wait a minute, I can just add or subtract these guys from one another, and I don't have to use a matrix solution. And so just pay attention to what you're doing. And sure, you can set up the matrix, you can solve the matrix, it works great. But if you don't need to, do it the easier way. And so this is an example of a problem where you don't need to solve the matrix.